Okay, so welcome everyone. We have a big day ahead of us. We'll be doing GPU programming. By the time this day is over, you'll be writing your own code. Okay, so there's a long journey to there. We'll start with sort of simple things, basic things. I want to make sure that you guys are on the same page. You understand what the architectures are, what the limitations are, what the different concepts are that are around concurrency and these kind of things, parallel programming in general. And we'll be using a new language, or almost a new language. It will be C. It's called CUDA, which is for programming GPUs. Now, you've heard of many things about GPUs up to now, and the most important thing to remember that even those who write CPU code today already count or forecast the possible computational things in terms of GPU hours, essentially. So you are thinking ahead and thinking about these new architectures, and I will explain to you why that is, why we are really heading toward a new world that will be essentially dominated by these GPUs. See if I can get my thing running. Okay, so before I get there, I probably have too many slides, but we have the whole afternoon. So if we spill over, that's okay. So before I get there, I wanted to show you very briefly how I got into this several years ago. It wasn't that long ago, I guess. Maybe 4 years ago, 3 years ago, something like that. And it all started with a project, an astronomy project, namely, this doesn't work, namely correlation function calculations. So we want to do spatial statistics of galaxies. And you have the usual relations that people look at, just a parallel-looking thing in 1 dimensions, a dozen bins or so. But when you have hundreds of millions of galaxies, isn't it a shame to just have this low resolution? I mean, you would like to get to something more refined, something that actually hopefully conveys more information. And in this particular case, we actually wanted to do something quite a bit different. So the state of the art to do these things on many or really large catalogs is tree algorithms. So in tree algorithms, you bin up your objects, and essentially you recurse the trees, and there are ways to recurse them in parallel, so we have a dual tree recursion. And you look at the buckets, so in these cells that contain at different levels of the tree, all the points that you want to look at. Now, these points will not have to looked at if all your pairs within those 2 buckets fit into one of these cells. Okay, so essentially, you can reduce the computation by looking at aggregates in the tree. The problem is when the bins get really small, then you essentially keep on going down and down on the tree, and eventually you lose all the benefit that your tree algorithms give you. So in particular, we were looking at something like this, some really high resolution thing, 800 by 800. So how do I do this? Okay, so I had to accept the fact that we probably have to do pretty much the brute force thing. So do I just run a big batch on our cluster downstairs and allocate 1,500 CPUs for this and run this really simple code, or try to figure out how to do it on a GPU? And because, well, we actually had time to run it once, but I figured this will have to be run multiple times. You will be making mistakes. You want to reprocess the data. So that was my motivation to actually get into GPU programming. And because we have learned already SQL Server, I wanted to show you what the design that we actually came up with eventually was to do the analysis for this astronomy paper. Okay, so what we did was we integrated SQL Server, the engine that I showed you before with the spatial statistics or the spatial search libraries, with a GPU that's in the same machine. So this is just a little framework we put together. Actually, it's been growing. And it's been used in genomics as well as astronomy now. It has a standard interprocess communication layer in between the two things, the GPU service, essentially, and the database engine, and they share a piece of memory through which they can communicate with each other. Okay, so I can run a query in the database, package my data in a piece of memory that looks just perfect for my GPU to be processed, and then ship it to the GPU, do the calculation, and then the results come back from the GPU. It's not the file that gets dumped on the file system, but actually it comes back in the memory, which I can just output as a table in the database. Okay, so that doesn't work. Okay, so it's all wrapped into user-defined functions. So you can have a function that says, I want the pair counts, histogramming essentially, out to some physical scale in megaparsec, and this is the number of bins I want to have, and this is the query, it's just a string, and this is the number of points that go in, so I know ahead of time how much memory to allocate, and so on. And just with this, that speeds back out a table that has essentially the bin ID, I, and j in 2 dimensions, and the counts, I can now calculate correlation functions in SQL. Okay, so I can call this function on the data, on the random, and the date random, and just combine them in SQL to create the correlation function estimation. Okay, so this is all running GPU underneath. And of course, you can do this with multiple GPUs, and you can create an asynchronous interface to it, so you can launch a bunch of these jobs against the GPUs, several GPUs in parallel, get some identifier for them. Where is it? I guess it doesn't work. Not turn on. Okay, that would help. And then once they are done, you come back for the results and then get the tables. Okay, so you can do these things fairly easily once the. So then, with a single GPU, a single card sitting in a desktop machine, we could process 600 trillion galaxy pairs. Okay, and that was what went into this paper measuring the BAO and the Baryon acoustic oscillations on the Sloan. All right, so the outline for today: we'll talk about parallelism, we'll talk about hardware, we'll talk about programming, we'll think about multi-threading and concurrency, and then on to GPUs. Okay, so that's my outline. So we look at, in particular, CUDA in the end, and we'll program as well in Thrust, which is a C++ wrapper over CUDA, simplifies much of the task that we have to solve. Okay, so really basic things. Parallelism. Well, you can have data parallel things, essentially divide up your data and run things in parallel independently on different pieces of the data. Okay. Or you can have task parallelism. That's when different actors essentially work on the same piece of data. Okay. Which one is simpler? Data, yes, because it's independent. So some people talk about embarrassingly parallel things. There's no such thing as embarrassingly parallel things. There are things that are simpler to do. So these are the simpler things to do. But there's always something involved, and parallelism is done. So you can have parallelism on all levels. Okay, so you have the cloud, you have clusters, you have machines, you have cores, you have threads. Okay, you will have parallelism everywhere on this scale, and you have to think about the whole architecture, the whole design when you write a piece of code. But we'll be operating down here essentially. How do I write a piece of code for a machine and make use of the cores and the GPUs and write threads that work in parallel and together? Okay, so some more useful terminology to get out. Scalability. There are things that scale up and things that scale out. Okay, so scaling up means you add more resources. You run this piece of code on a bigger computer. Okay, so that's the easier part. Scaling out horizontally means that you keep on adding machines. Essentially, you have more of the threads, you have more of the computers, you have more of the. It's not a bigger computer; it's more computers. Okay. So for a while, people thought that scaling up was important. Now, I mean, scaling out is clearly the trend, and you'll see why. Okay. So on the cluster, I won't talk about this too much. You have the HPC clusters that you are probably already familiar with. You launch your jobs with PBS, the way you learned it earlier this week or last week, I guess, and use MPI to communicate between the nodes if you have to. Okay, so the machines can chunk on, so just crunch on the machines independently, or if they have to talk to each other, then use MPI, message passing interface. Okay, and the queuing system is where you submit these jobs. Okay, like PBS. Okay, we actually will be using PBS. So in this afternoon, we'll be accessing a cluster of GPUs, and you'll be using PBS much like the way you did it before on Condor. And that will be the mechanism to get at the machines with the GPUs. So I hope that you remember this. All right. And then you have the computer level, where there are different kinds of parallel computers, and there is, in fact, a whole classification scheme for them. Okay, so that's called Flynn's taxonomy. And you do it by essentially looking at what they do and what they do it on. Okay, so instructions and data. You can have single instruction, single data computers. That's the standard, the classical von Neumann computer, right? That's what we are all used to programming, essentially. You're thinking about step by step going through your program, fetching data, doing something with it, outputting the data. So that's SISD. Okay. Now you have multiple instructions, single data. That's very rare. But there are some machines like that, I was told. I haven't seen one yet. What's more important, and this is what we'll talk about mostly today, is single instruction, multiple data. Okay. So you have a single instruction coming in, actually works on multiple data in parallel. So these are kind of like the vector computers and the GPUs today. In fact, there are extensions to the x86 architecture that have been using this for a long time. Okay. All right. So there are, of course, the MIMD, when the multiple instruction, multiple data. These things on the right are quite rare these days, I guess. I could be wrong, but. Okay, so how does it look like? So just the schematics for this. Okay, so this is the classical computer. There is the instruction coming in on the left. There's the data coming in, and you outputting data. Okay, very simple. Okay. SIMD. Again, instructions are flowing into the processor. That's your program. The data are coming in as well, and then you're outputting results. But it's a vector computer. It's getting lots of things done at the same time. Okay. So the extensions that I mentioned for x86 include the MMX, the MMX2, the SSE, the different kinds of multimedia type of things that Intel has been putting into these processors and AMD. And of course, GPU programming. So that's the same paradigm as well. So we'll be doing programming that will do this, right? So one piece of code running on lots of data. Okay. So I wanted to talk a little bit about parallelism and Amdahl's law. I mean, he has several laws and rules of thumb, how you should design your program, what the computer should be doing, how much operation it will have to do per data, and so on. What's interesting about this law, which is what people mostly talk about, I guess, is that it actually has a very interesting implication for what you can achieve with parallel programming. Okay, so here what I have is essentially a piece of code that is partitioned into two parts. The part that you can execute in serial, in sequentially only. Okay, you always have things that you can, reading a file perhaps or something like that. That is just a sequential execution. There's part that you can parallelize, like a for loop, but that's the simplest thing, maybe if there's independence. Okay, so if you want on a single core, single thread, single computer, then the time it takes is S plus P, and the whole thing has to run. Okay, if you run it on N devices or N threads, then it takes S, which is the sequential part. You can't have much, you can't do much with that, and you do the P, but that's divided by N because that's resources that you have. So if you just quickly rearrange this and introduce a variable that is the fraction, so little p is just a fraction of the parallel processing, then you arrive at this equation. Okay, that tells you that what your possible gain is. Okay, so if your n goes to infinity, this term disappears. Okay, so if your code had 20% code, 20% of sequential code that you cannot parallelize, then you have here 0.8. Right, the 1 minus p is going to be 0.8, and you see that that's the best you can do, right? So your maximum speed up is going to be a factor of 5, right? So yes, 20%. So I mean, essentially parallel part goes away, so the sequential part remains. So it's very counterintuitive, but sometimes when people want to optimize their code and go and do the parallel coding, what they do first is they actually optimize the sequential part, right? To see how fast you can make it go. There's no point writing a parallel code if the only thing that you gain is a factor of 2, right? And this will tell you. Of course, this is it's becoming a theme now. The bird is back. I have no food. I have coffee. Okay. I have to keep on going, I guess. So, where was I? So essentially, you look at your problem, and if you see that there's nothing to be gained by running it in 100,000 computers, then there's no point doing anything. There's no point launching into GPU programming. There's no point applying for supercomputer time. So first you have to figure out how fast you can make it. So this is very optimistic. Of course, there's overhead involved with parallelism. So you have to remember that this is a formula that is really optimistic. Okay. Okay, so let's get to the chip. Now we're getting close to the GPUs. Okay, so you have seen Moore's law before. This is the curve that shows you how the number of transistors on a chip go up over time. It's a log-log plot, so it's a log-lean plot. It's an exponential curve. Okay, so that's the exponential growth that we have talked about quite a bit. So what's interesting about this is that this curve is truly happening, and it's actually applicable to the near future. However, there's a new cap. There's a new limitation that we have to obey. And designers of the chips actually have to design their devices around these. And that's limitation of energy. How much power you can pump into these things is limited. It's for several reasons. Okay, so computers are still getting faster, but that's almost an incremental change as they tune the processors a little bit. We don't actually get quite the speed that we used to. All right, so the interesting thing that we notice is that if you wanted to do, say, decode a video, okay, play an MPEG-4 high-definition movie. If you do it on your computer with a Pentium processor or what you have, it's going to take 10 times more power than if you did that on a special DSP, digital signal processing unit. Okay. If you wanted to do it on a custom chip that was designed to decode that video, that's another factor of 10. Okay, so going from a general purpose device to a specialized device is a factor of 100 in power. Okay, that you actually, it's quite astonishing if you think about it. Okay, so this also means that the designs are becoming very different. So you have smaller cores and many of them. Okay, and they will be all packed on the same die, and you can turn them on and off. And they will be slower. I mean, the clocks are typically slower these days than they used to be. They sort of leveled up at 3 gigahertz, but most machines are actually slower than that quite a bit. Okay. just again for energy reasons. Okay. So this is a slide I kind of borrowed from Andrew Chen, who was vice president of Intel Research, and now he's at San Diego, here at UC San Diego. He talks about... Used to be. He's not anymore.
University of Chicago.
I did not know that. Okay, that's interesting. So he talks about this 10 by 10 new design that's replacing sort of the old general purpose thing. So just to sum it up, essentially what we are talking about is big general purpose devices that have grown over time since the beginning of time, definitely since the 90s. Essentially the Intel chips, the x86 architecture is getting thicker and thicker and wider. More tools are packed into this general purpose device, and keeping the backward compatibility and all that. It's a kind of hurdle as well. And switching that to a completely new architecture, a new design, where you have tools available for every task that you would want to do. Okay, so instead of having a general purpose code or CPU and special software running to do the special things, you just turn on and off essentially the parts on your chip that do the specialized things. Okay, so you might think this is futuristic, but every one of your cell phone does this already. Okay, so this is already happening, and this is potentially where the desktops are going as well. Okay, so what you have here is essentially one live component that is turned on, and then the rest of it is dark silicon. Okay, so the transistors are there. You still have Moore's law, but they're not running most of the time. You only run things that you need. Okay, so that's scary to me. Okay, because then if you don't have general purpose computing, then how do you do science on these things? Like, how do you run your analysis on an MPEG-4 encoder? Okay, so you have to think about this. So what's the way out? What if overall computers are going to become one of these things? The CPU is shrinking, is going to be a corner of the desktop. No? Not anyone? So I think the answer is the GPUs. Okay. So the GPUs used to be specialized devices, and they're becoming general purpose. Okay. And the reason is gaming. So if you're a gamer, then thank you for this, right? I mean, the gamers are driving this market. Okay. So they want to simulate the real world. Okay. So the virtual world on the GPUs essentially drive all this general purpose computing, so that everything now is happening in the GPU. You don't have to go back and forth with the CPU to do an explosion of a grenade in your game or something like that. Okay, shock waves, everything like this. Now it's running on this. So that's where the GPUs are coming from, and they are really good at what they do. They are lean and mean crunching machines. This is an old slide again. So I used to say that there is 512 cores on a card, and you can have 25,000 threads running in parallel. But that was the Fermi architecture. I'll talk about this a little bit more. Okay, so now the latest video cards have 3 times more. Okay, so you're talking about 75,000 threads running on a single GPU in parallel. Okay. That also means that all the algorithms that we built over time for these von Neumann computers are pretty much obsolete. You have to rethink your strategies. You have to rethink the algorithms. And it's not always obvious what the good strategy is. So just to give you an example, you all learned about sorting probably, how you sort big arrays. And well, it turns out that the algorithms that we learned, and quick sort and deep sort, and they are not really that fast anymore. On GPUs, there's something else. It's called a radix sort, or a modified version of that. And that's the fastest sorter there is today. So they can sort 1 billion keys a second. That's the rate on a GPU, which I think is astonishing. So if you want to do sorting, indexing, best on a GPU. Okay, so the reason why the old algorithms are wrong or just really not designed for these new machines is that they assume that the memory is fast and the CPU is slow. Okay, and now it's backwards. Okay. If you have to go to memory, it takes a long time. If you want to do some computing, that's almost free, especially on the GPUs. The GPUs have very high bandwidth. You can talk to the onboard global memory, at about 200 gigabytes a second. Is that right? And yet, most of the cores are usually starving. So they don't have enough data. It's really hard to write code that makes use of all the cores and all the GPUs that there are. So that's usually the challenge. How do you feed the GPU with enough data to actually do enough computing? And when they do, you know it. The temperature goes up and the machine starts lifting up. Okay. All right. So one more thing. Mentioned Moore's law before. Now the interesting thing with GPUs is that they are actually on a different curve. Okay. So we have the exponential growth, but because they are allocating the silicon in a different way, they actually can do a whole lot more computation. So here what you have is essentially a standard traditional CPU with the arithmetic logic units, essentially a 4-core unit, sitting in the corner. And there's all these control logic and cache and of course the RAM that is trying to essentially feed these CPUs as efficiently as possible and doing all sorts of crazy things like out-of-order execution and things like that, just because we are writing sequential code and they try to speed that up. Right? So there's lots of logic going into that. And there's lots of cache as well to just speed things up. Essentially, you don't have to go all the way to here. Okay, so they try to do the smart thing for you, but even then you have to remember this architecture to write fast code. I mean, many people write just a for loop this way or that way, and you realize, there's a factor of 10 in performance or more. Okay, so you have to be careful, even with the CPU code. I mean, people criticize GPUs for that. To write fast GPU code, you have to understand the architecture. I would argue to write fast CPU code, you have to understand the architecture as well. So there's no difference in that. There's certainly much more logic, put in work for you, but it's not perfect. So what you have here, though, is lots of computing resources. Okay, very little control and cache per cores, but the memories are typically the same ballpark. Okay, not quite yet, but there is quite a bit of RAM on these GPUs as well, up to 6 gig or more now. So as long as you can feed these processing units, you can do a lot with this. All right. So let's talk about programming a little bit. And any questions? Feel free to interrupt me anytime. Okay. So, there are lots of programming languages. And you really should be learning a new language only when you actually get something new out of it. Okay. So I think CUDA is one of those languages. So by the time you learn CUDA, or by the end of this day, you will actually have a better understanding how these machines work and why the language is like that. Okay, so all right. So there is assembly. Okay, you should never write assembly. Okay, maybe for a hobby project if you really want to learn what this is about. This is sort of the lowest level programming, almost the lowest level, very close to the machine. But it's a pain, and it's different for all computers. So yeah, you should never go there unless it's really necessary. All right. And there is C. And C is a great language. It's quite high level in the sense that it's readable and you can write abstract things in it. But it's still very close to the hardware. Okay, so you get to access the iron as is, and we'll talk about C. Who knows C? Oh, cool. All right, very good. So we'll make good progress. If you don't, that's okay. You do? Okay. Okay, that's fine. You learn it quick. Okay, so essentially everything that there is written in C. I mean, there are some other things. There are some new things that are not written in C, but usually they end up being written in C if they had to do high performance things. Okay, in science we had Fortran, but that's a side issue. We not discuss that today. Okay, and there's Java, and there's Python, and all the others. Okay. Okay, so this is for you. Okay. So this is how a C code looks like. Okay, you have some libraries you want to use, the header files that tell you what the functions are, and there's an entry point where your code starts running, and again, here comes the sequence of commands. Okay, and every command will do one thing. Okay, so what does this program print? Yes? Prints 1. Okay. How about this? Oh no. Okay. So here's So I have no chocolate. Sorry. So you have header files. That's where the declarations are, and you have the source that essentially is the actual code. And when you build an application, you compile it and you link it. Same thing with the GPUs. Okay. So we have to do the same. Okay. So pointers. The pointers are very interesting and very important, and we will use them for the GPUs. So here's an example that runs just normal C code. As very simple C code, but it uses pointers. So what does this print? I meant to mask out my comment. It's helping you too much. Sorry? It prints 1 again. Why? Sorry? Right. So that's right. So the answer was correct. I just wanted to say why. Well, ask why. So yeah, indeed. So what happens here is that you have a piece of memory that you refer to as X, okay, and then you steal its pointer. So the pointer is the one that tells you where things are in memory. Okay, this is very important. GPUs, that's how GPUs will work. Okay, so the pointer tells you where things are in memory. So that really is something that just points to the memory. So that's P as the pointer. So if I change the value of X, okay, then the memory that's sitting under the pointer is going to change. So the value will change there. Okay, so when I fetch the value, the star P is how you get the value at the pointer. Okay. When I fetch that value, having done this arithmetics there, I will get actually the new value. Okay, that's under the pointer. So everybody understands this? This is critical. So these are the kind of things that you will have to do with the GPUs. Okay, I should have masked out the commands. It's harder that way, maybe. Okay, but that's right. So that's how it works. All right, so arrays. Okay, it's not that you should use arrays like this. I just wanted to show you how arrays would work. So it's again an example how you use pointers in C. Okay, so very quickly let's walk through this code. Okay. So there's just a declaration how many elements you want in a vector. Here you have a pointer, point somewhere, okay, that actually is a whole sequence of floats. So the num is the number of floats, and you allocate memory for this many floats. The size of floats is how many bytes a float is. And essentially by knowing how many things are and where they start in memory, you can get those data values. Okay. So here I'm adding up, so filling up this array, this piece of memory that I just allocated with some values. Now it's just I squared, okay? But what this really translates to is is this, right? The value at the pointer plus this many elements. So this is an integer, this is a pointer. It's called pointer arithmetics. Okay, this is very important again for GPUs. Okay, so what happens is p plus I is again a pointer to the ith element, okay, and the star is the value underneath that you can get. Okay, and so if I do this, pointer plus the num minus 1, indexes start with 0, okay, then this is going to be a new pointer that actually points the last element. Okay, so star p is the first element of the vector or the array, and then star q is the last element of the array. Okay, so this is just very basic pointer arithmetics. Okay, that said, when you do linear algebra, you should be using the BLAS packages for the reasons that have been discussed before. But this is how, very simply you can do these kind of things. And then you have to free up the memory as well. So once you're done with your analysis, very serious analysis, then you can just free up the memory. Same thing with the CUDA, you'll see. Okay, so this is one more example just to take it one step ahead. And again, not that you should use matrices like this, but you have to understand that there are pointers to pointers. Okay, because the pointer itself that points somewhere in memory is also just a piece of data that's sitting somewhere in memory. So you can point to that as well. Okay, so you can have pointers to pointers. So in this case, we have a matrix created where we allocate essentially, so n by m matrix. Okay, we allocate enough memory just linearly. Okay, with this many bytes, so we know how much we need to allocate, and then we allocate an array of pointers that tells us where the first element of each row is. Okay. You don't have to have this, but it's just a convenience. You'll see why. So you have now a vector of pointers that tells you where each of the rows start in your matrix. Remember, in memory, it's just a big linear thing. Okay. Any questions about this? So then I can set these pointers. Okay. So again, V is my linear memory allocated. A is the pointer to pointer, the vector of pointers. So AI is just going to be the starting point of my memory allocated, plus I times m. M is the length of my row. Okay, so again, A0 is going to be the first element, the pointer to the first pointer, and then you increment it by m. That's the first, second, so zeroth row, first row, second row, and so on. Okay, and then you can just load some data either using the v pointers or using the m pointer or the a pointers. So then you're done. So you can loop through I and m and print out aij. You see, this is ai is going to be a pointer. So a is a pointer to pointer. AI is going to be a pointer, and aij is going to be the value. Okay, so the ij value of the A matrix. Okay, is this strange or new to anyone? No, good. Okay, so this is how things work with the pointer. So if you understand this example, then you will understand how, no? Okay?
It's terrible.
It's terrible. Well, if you think about it, this is what happens in the computer, right? So you are just one step. I mean, if you're used to programming in Java, or I don't know what you prefer. Do you program in Python? Python. Python does the same thing. Like the NumPy library will be doing these kind of things underneath, right? If you are a good Python programmer, right, you never write a for loop, right? Why? Because in Python, it's an interpreted language. In Python, everything takes forever to get to the data. You have to go through a zillion layers. So if you're a good Python programmer, you're using these vectorized techniques. You're using maps and zips and lambdas and things like that. Okay? Because all these for loops will be running underneath in C, right? So in many ways, Okay, so in many ways, this is the low level where you actually have control over things, and Python is a high level thing where you just issue like, oh, I really mean to do this. I don't want to run a for loop. I just want to do this. Okay, so all right, and then of course we have to free up both the pointer to pointer array and the actual memory allocation. Okay. They are both actual memory allocations. You need actual memory allocated for the pointers as well. Okay. It's not that bad. This is how your computer works. Okay. Any more questions? No. All right, so let's talk about the concurrency just a little bit. And this is because things get complicated when you have multiple actors. Okay. So again, like I said, there is no embarrassingly parallel problem. So that the data parallelism is the simplest thing you can get when you process things independently. The next simplest thing you can do is map reduce, right? So you do the data parallel things as a map process, and then you reduce things. Okay, it's really simple. It's the next simplest thing. Okay, it's not a program. It's not a framework. It's a pattern that you can implement. And in fact, we'll do it in CUDA. Right? This is a very simple idea. All right, so there is the elevator problem. Okay, so my grandma lives in a really old house. Has a really old elevator. Okay, endless fun for a kid. So you walk up to this elevator. It has a button and two lights, green and red. Okay, so you walk the elevator. You press the button. The green light comes on. Elevator comes. You get in the elevator and you press the button. And you go to the floor you want to go. That's the usual thing how elevators work, right? Okay. Now, if you walk up to the elevator, you press the button, nothing happens because the red light is on. It means that somebody is using the elevator. Okay. So if there was no mutual exclusion on that elevator, this shared resource that multiple people want to use at the same time, then the elevator would come, right? And then whoever is sitting in the elevator, hoping to go to the ground floor, will come to the fourth floor to pick me up. So that would be terrible. So instead, whoever is using the elevator goes down, and when that happened, it will come and pick me up. Well, except it's an old elevator, so it doesn't actually come and pick me up. I have to wait there and wait for the red light to go away, and then race. Right? Whoever, if there are 5 people on different floors, they stand there and they wait for the light to go, and then hit the button. If you are first, you get the elevator. If you're not, then you have to wait. Now, literally, that's how it works. Exactly. So if you think this is a simple problem, think again. So this is we don't think about this because our elevators are fairly sophisticated about it, but not every one of them. And there are, in fact, several. There has been zillions of theses projects written about this problem, and this is still something that you can improve on. Imagine you have a really tall building and lots of people want to go up and down. You want to collect them going down, collect them going up, or all the things you can imagine. So this is not a simple problem. So the reason is that you have a shared resource. Multiple people, multiple actors try to do something with a shared resource, and that's where you have to do simple things. So the simplest thing you can do is this mutual exclusion, right? That's even this 75-year-old elevator has. That somebody is traveling in the elevator, then she shouldn't be called away, right? It's in use. So that's the simplest thing you can do. It's called locking, and you can lock anything really. So, of course, what happens is that people have to wait for each other, right? So this is where the complications come in as soon as you lose the data parallelism, that you really have to think about who's using what and when. All right, so if you haven't heard about this is a classic problem. This is very important. Right, so the philosophers or the starving philosophers, I don't know how you. So the problem is the following. There are 5 silent, they don't talk typically, sitting at the table. Okay, all they want to do is think and eat. They have to eat so that they can live longer, and they can do this forever. As long as they eat and think, then they can do this forever. Okay, so this arrangement is such that they have forks, left and right, but every one of them needs both forks to eat. Okay, so you can't just eat with one fork. It's spaghetti, so I guess you need some sort of. Okay, so then. You can come up with a scenario. imagine this. Okay, so they need both forks to eat. Okay, so now we have to write a piece of code, or design an algorithm that they can execute. Okay, in parallel. So they will just follow this prescription what they should be doing, so that they can eat and think and eat and think. So that they all live happily ever after. Okay. So you can think of a program that says, pick up the right fork, and then think and wait until the left fork, okay, so let's start from the beginning. So you're sitting there, you're thinking, so think until the right fork becomes available. Okay. Then you pick it up. Then think until the left fork becomes available, okay, and pick it up. And then eat, and then put down the right fork, put down the left fork. Right? So that's a very simple sequential program you can imagine. Now, what happens if you run this in parallel? Okay. So this is the kind of thing you have to think about. So now, 5 philosophers all start doing the same thing at the same time. So think until the right fork is available. They look, oh, it's available. So they all pick up the right fork. Okay, now wait until the left fork becomes available. Okay, so they will be waiting for a long time. Right, so that's called a deadlock. Okay, so now there's nothing. Your computer is frozen. It's doing nothing. It's waiting. Okay, these things happen in software. This is the kind of thing, the most simple thing but also the most complicated that can happen. So this is also an interesting problem, kind of like the elevator problem that people have been thinking about for a long time. And of course, there are different kinds of solutions, and depending on what your constraints are, you can come up with different ideas. So, for example, you can have, simplest thing is you can have a waiter, that sits or just stands around, and essentially wherever the waiter goes, if he's here, then he gets to eat. If he's here, then he gets to eat. If he's here, then he gets to eat. You get the idea, right? So it is like some sort of control over like who gets to do what. But there are different kinds of solutions to this, and if you're interested in this, then you should definitely look into it, because it's an interesting and fun problem. Okay. Any questions about this? Okay. So parallel threads. And now we are down to what we want to do. So we want to write parallel threads for the GPU. So this is a parallelism that happens in the machine. So a single core, even your x83, 86 machine, your processors will run 1 or 2 threads, and you have multiple cores. So, all right. And again, you have the different parallelism. If it's data parallelism, then good luck. Then it's easy. If task parallelism, then you have to think, because they share the memory, they share the I/O, they share lots of things. So you have to be careful how they talk to these things. Okay. This you have seen before. Then I talked about how they are different. Now, what you should observe now is that this thing has 4 and this thing has 500. Okay, so you have 4 competing philosophers, and here you have 500 competing philosophers. That's a very different scenario. Okay, because if the waiter goes around, and there are only 4 philosophers or 5 philosophers, then your efficiency goes down by a factor of 5. If you have 500 and they all have to line up for to eat, that doesn't make sense, right? So then you have thrown away your parallelism. And so anyway, so there are lots of threads, right? So now we are there where we want it to be. So let's write code for the GPU. Okay, we don't write code for the GPU. We write code for the hybrid machine, right? So this is a CPU and GPU combination. You never have just GPU. You have the CPU that's sort of arranging all the things, reading files, talking to the network, loading the memory, and then farming out jobs to the GPU. So what happens is in a GPU program is that you have a CPU thread. Okay, you have a CPU thread running on the host. That's your computer. The host is your CPU, essentially. You have your main function, just like we had it before, okay, in the C code that starts running. And this thread runs. And then, at some point of your execution, you have your data loaded, you have everything ready to go, where you load this onto the GPU, and then you fire up zillions of parallel threads on the GPU, and that's called a kernel launch. Okay. You write a piece of C-looking code, that's CUDA, that is called a kernel, and that kernel will run in all the threads, and all the blocks, and all the machines that there is. So now, once that launch happened, right, that's running. You don't have to worry about it anymore. You don't sit around waiting. Your C code, your main function keeps on running. Okay. So you can just keep on processing things. This was instantaneous. You just fired up this launch. The GPU is working for you. But then you can keep on doing your CPU stuff. And then when you need the results of the GPU processing, then you just sync. Okay, so you say, okay, now let me wait for the GPU to come back. And when the GPU comes back, then you can again fetch the results from the GPU. And so on. Excuse me. So this is very important, right? You can see on forums like here, okay, the GPUs are so fast. Let's have Linux running on the GPU. Okay, let's throw away the CPUs. We don't need them anymore. Yeah, it just doesn't make sense, right? They can get smaller, and that's what's happening. But you need the CPU essentially to take care of the basic things around. Okay. So you can program GPUs different ways, and there are different wrappers around them. There's CUDA, which I really like, and that's what I want to teach you because it's flexible, it's high performance, it has access to the low-level routines, as well as gives you very high-level programming interfaces. So, for example, you have all the usual libraries like BLAS available for CUDA. There's OpenCL, there's direct compute, there is other things, there are new things coming out every day. So this is definitely going to be the future of computing. Now, which one of these is going to win? I don't know and I don't care. But CUDA is definitely a language that you can learn today and benefit a lot from understanding how these devices work. And all the others will do the same, right? The syntax might change a little bit, but those are incremental changes. And even if you can parallelize for loops with just pragmas in a language, the bottlenecks and the design constraints are always the same. Okay. So CUDA. All right. So this is something that's happening on a big scale. You should go to CUDAZone.com. At CUDAZone, I can't remember what the website is. If you look for CUDAZone, sorry. Yeah, NVIDIA has it. Yeah, on NVIDIA's website, they have the CUDA zone. So zillions of research projects that are essentially codes with white papers and research papers. It's all together. NVIDIA also gives you a very nice SDK, a development kit that you can download and look at all the examples for pretty much everything from image processing to simulations and body simulations and so on and so on. So it's a very impressive website, and I recommend that you go there and look around, and maybe you already find something that is very similar to what you are planning to do. All right, so what's currently available, against last year's slide, but I'm sure there are more things since then, is a bunch of libraries for sorting, random number generation, the BLAS, FFT, Hadamard transforms, lots of things, video encoding, decoding, you name it, it's there. And you can just use these libraries essentially as if you were programming CPUs, because these are just really API calls, except the computation is happening on GPUs. But then, if you have to, you can always write a custom query or a custom piece of CUDA code that actually drills into the GPU memory and does what you want to do in place, and then keep on running your high-level routines. So, all right, I may as well tell you this is the bad news if you like Linux. The best debugger available for CUDA is on Windows. That's where games are developed. That's where the nicest development environments are, and this is also where the best debugger is. Okay, but I asked the question how many people debug code on the first day. There weren't that many people, so that's okay. It's good to have good debuggers, though. I mean, I don't actually have anything running right now. Usually, I show in the debugger how the code runs, and I just have to do it on the whiteboard, explain to you later in this afternoon how the codes run. So there are imaging routines. There is a wrapper for Python. It turns out the Python wrapper actually is, well, it looks as if it were a Python wrapper, but when you actually write the GPU code, you write CUDA code. Okay, and just a string that compiles essentially at runtime. So what you learn here today is also applicable to the PyCUDA stuff. And there is also high-level programming in C++ with Thrust. I'll talk about that as well because it's very powerful and very simple to use. All right, so some terminology before we break for just to get some words out. So the Fermi is the name of the previous architecture. Previous meaning, early this year and previous years. So this is where are the cards that we'll be programming as well. So we'll be looking at the C2060. So these are cards with 400 plus cores and about 3 gig of RAM. Now, what's important about this family of cards for for scientists and us is that they actually have, for the first time, they have the standard floating point arithmetics implemented. Okay, so now if you run, so before they didn't have the same calculations, they were still floating point calculations, but it wasn't the exact same algorithm that the IEEE standard defines. This means that now if you run something on the GPU and on the CPU, the two things will be the same. Okay, so bit to bit. And that's important because now you can easier verify that your calculations are correct, or you can match your CPU code and so on to the GPU. So that's Fermi. The latest generation just was announced at GTC in May, GPU Technology Conference, is the Kepler. Okay, and this is the greatest and latest and fastest and better than Fermi. Fermi was already pretty good. So now we are talking about 1,500 cores on a single GPU. You can get a card with 2 GPUs. Only does 3,000 cores, 150,000 threads in one card. That's scary. Okay, so which device? There's 2 lines of cards, and they are different in price by a factor of 10. So you want to know which one is which. There's a Tesla line. That's the high-performance computing cards that are typically installed in these clusters, and these are the cards that are mostly designed for computation. Okay, some people game on them, but they have more memory. They have error-correcting memory, and they have more double precision units. So if you want to do double precision a lot, then these are the cards of choice. They also are built to run a little slower, a little bit less cores, so that they can run all the time. So you can just run these things till their life is end. I mean, it's just there's no complications. Now the gaming cards are cheap. Okay, so these are the ones that you can have in your desktop, no problem, and they are pretty decent memory. They have 1.5 gig easily. I mean, there's pretty much no memory card at this point that has less than 1 gig of memory. So that's not that much difference with the 6 gig. And in fact, they run faster because they are designed for the bleeding edge. And they have sometimes more cores. So what happens is that if you run scientific computation on these, which is not recommended by NVIDIA, I do, then you can potentially fry them. I mean, the cards are designed for the 60 frames per sec games where there's enough time between frames that the heat can dissipate. So I haven't been able to fry one, but potentially they said that you could if you can really feed the GPU with lots of computation, then you can fry them. But these are great cards, and these are very good for development. So you should have one. You all should have one. What is this about? Okay, let's skip this one. So terminology. Okay, so the kernel I already mentioned before. This is the GPU code, right? This is the same piece of code that runs on all the cores on the GPU. So what they do is they pick their piece of data, they work on it, and then they write the results. Okay. We'll look at these in detail. They are almost like normal C, but they have some special limitations. Okay. The threads on the hardware are grouped into warps, which is 32 threads. So you cannot, there's a device, it's an SIMD device, it cannot run just one thread. It can run one thread, but it will be running essentially 32 with 31 idling. Okay? So these are really built to do lots of parallel computing. And what you really want to know about is the block. This is the logical, not just logical, physical unit of threads that can actually collaborate. So threads within a block actually can talk to each other through shared memory and so on. We'll talk about this more. And so a block of threads can be organized usually in 1D, 2D, or 3D such that it matches your data. If you have 1D data, if you have 2D data, 3D data, you can arrange your threads to match that geometry. You'll see how this works. And the grid is essentially a bunch of blocks. And essentially what you do is when you launch a kernel, you launch a grid. I can reiterate on these a little bit more, but I'm running out of time. So maybe I'll just keep on going. And if you have questions, just interrupt me anytime. So the grid is very important. This is the grid of blocks that actually has the whole problem that you want to launch at once. Okay. And this is, again, the same type of thing. It matches the geometry of your data, so you can chop it up. If you have this much data, then you can, and the block is limited to this big, then you can just have multiple blocks. Okay, that's your grid. And the beauty of this is that now, with many blocks in the grid, you can actually, run these in any order you like. If you have a device that can run 2 blocks at a time, that's fine. Right? It will just do 2 blocks at a time. If you can run 4 at a time, that's fine, and so on. So there's no, when you launch a kernel, there is no guarantee that block 1 will run first and block 30 will run last, or 10,000 will run last. They can be run at any time. The optimizer, the pipeline optimizer, will decide which one runs first and which one runs. They can be interleaved and so on. So, well, they actually can, but the only thing is that the threads within a block can talk to each other, okay, and threads across blocks cannot, okay, and that's because they could be running at different times, okay. But this is how you can scale things up, right? So this is how you can scale things up and out. If you have a bigger card, then you just have multiple blocks, and so on. Okay, so this is how a hello world looks. So you have your C code, the usual main function that starts out with the usual stuff. And then at some point you say, okay, now here I want to run my kernel. And my kernel gets pointers, A, B, and C. And it will add A and B and save the results in C. Okay, so here's a magic construct here that says how many threads to run, essentially. We'll look at this in detail. And then this is how your kernel definition looks like. It's just like a piece of C, but it has this global keyword in front of it. And that's what determines this is a kernel that will be running in parallel on the GPU. So you get the pointers, and each thread can figure out who it is based on built-in variables. Okay? And essentially figuring out which piece of data they should be running on, they can just do it essentially a single addition. So in this case, you're running n threads in parallel. Okay? Every thread loads one element of the A vector, one element of the B vector, adds them together on the GPU, and then saves it into the element of the C. Okay? So these lines will be running in parallel. Okay, so we look into this very detail, in very much lots of detail. All right, so now I'm getting into how this actually looks in CUDA. Is this a good time to stop and continue And so maybe this is where I will continue, and we'll do a very quick recap on the basic things. Any questions on this so far? Okay. Yes. Difference between what? The test? Price? Oh, price. Oh, sorry. Yes, price. Yes. So the GeForce cards are, a few $100s typically, and the high-end ones maybe $5. The latest and greatest and fastest. And these are actually the fastest cards there are in the world, right? Because they have more cores and higher clocks. The Teslas are more like 3,000. Okay, and they have bigger, better cooling and little lower clocks and more memory. They have error correcting. So they are important differences. The error correcting memory that can be turned on and off, and they have something else I forgot. Oh, double precisions. Yeah, so they have more units to do double precisions. Okay. Yeah. Yeah.
How's the clock loaded first into the RAM of the computer and then pass it to the RAM of the video card, or can you just classify it?
Well, exactly. So what you do is typically that you load it into the host memory, into just normal CPU, just normal memory on the machine, and then you load that from all the GPU memory from there. You can potentially transfer data between GPUs. These are recent things, but well, that's usually the standard pattern that you could just have a piece of host memory and transfer it to the device. Yeah, we'll look at this. You'll see this in action. Okay, so if no more questions, then we'll continue from here. Thank you.